Welcome back, students. In this video segment, we will consider one section, section 4.2, entitled The Law of Sines. The Law of Sines. To give you an idea of what's going on, what I'd like to do is sort of segue into this topic by looking first at something we've already done and then modifying it to sort of create a need for something new. So before, we used trigonometry to solve some pretty practical problems. In fact, trigonometry is used everywhere in the sciences, to solve a lot of practical problems. But here's a real simple one. Before, the question might be, find the height of the tree. Find the height of the tree, where we're given the angle of elevation up to the top of the tree, using the shadow cast by the sun, and the distance from that point at which the tip of the shadow is to the sun to the tree is 150 feet. Now we had to make a really, really big assumption, and that really, really big assumption that was that tree was growing right out of the ground at a right angle, which, as I understand it, never really happens exactly. Trees don't pop out of the ground at exactly a right angle. Maybe some approximately a right angle, but this is not a real practical problem. It doesn't allow for the idea that specifically for our purpose, that a tree might be growing out of the ground in some angle that's not a right angle. And we solved this problem under this really restricted circumstance. We solved this problem just by using the one of the trig functions. So if we call the height of the tree, let's say h, let's do that. Let's call the height of the tree h. Then we're looking for the vertical leg of a right triangle. And we're given the adjacent side to 22 degrees and the angle 22. So we would use which trig function to do this? Which trig function would we use to solve for the height? We would use the tangent function. So we would use h over 150, that's opposite over adjacent, equals the tangent of 22 degrees. Then we would multiply both sides by 150. So h equals then 150 times the tangent of 22 degrees. Okay, then we would put this into our calculator and find that h is approximately, and I did this and I got about 60.6, rounding to one decimal place, 60.6 feet. Okay, without any problem. This was one of the easier types of problems we did in section 4.1. Well, we want to change the problem up a little bit. In this section and the next section, we want to consider more realistic kinds of situations. So let's say, now find the length of the tree. Notice I didn't say the height of the tree. I want to find how long this tree is. And the new situation is the tree is growing out of the ground at an angle of 104 degrees pictured there. The angle of elevation up to the sun is still 22, and the distance to the base is 150. We can't use the trigonometry that we've learned so far in this course to find the length of this tree. Why not? Well, because the 6 trig functions depend on, if we're going to use the 6 trig functions in triangles, depend on the triangle being a right triangle. So what we do in this section and the next section is we will solve oblique triangles. We will solve triangles. We'll develop 2 very simple techniques that can be used to solve triangles that don't have right angles in them, oblique triangles. Okay. In section 4.2, we look at something called the law of sines. The law of sines. Law of sines. And in 4.3, we look at something called the law of cosines. These 2 laws are used to solve oblique triangles, but they're used to solve separate cases. So we use the law of sines to solve certain cases that are given in the law of cosines for other cases. So I'm going to show you the cases where we would use each of these laws, and then I'll describe what I mean by this notation. We use the law of sines to solve cases in which we are given an angle, a side, and an angle, a side, an angle, and an angle, and a side, and an angle. I'll explain the notation in just a minute or so. We would use the law of cosines to solve the only other possible cases. We're given a side, an angle, and a side, and we're given all three sides of the triangle. Notice what's missing is angle, angle, angle. And we mentioned this very early in the course, that you can completely solve a triangle if you're given any three pieces of the triangle, with a small exception that one of those pieces has to be a side. So it's impossible to solve a triangle if you're given all three angles. We have to be given a side. So what does this notation mean? Well, the notation angle, side, angle means that we're given two angles in the triangle. So we're given two angles. I guess I could draw a little bigger here. We're given, say, 15 degrees, and let's say 32 degrees, and we're given a side that's contained between those two angles, let's say 10 feet. So this would be the case angle, side, angle. The case side, angle, angle is different, even though we're still given the same type of information. We're given the side and two angles. So let's redraw this. We would be given, say, 10 feet. There's a side. Let's say 32 degrees and 97 degrees. We're given two angles, an angle and an angle, but and a side, but the side is not between the two angles. Okay, and of course, side, side, angle means we're given two sides. And let's say this is 5 feet, this is 4 feet, and this is, say, 25 degrees. We're given two sides and an angle that's not between those two sides. Okay, so of course, side, angle, side would be we're given the two sides again. So let's say 5 feet, 4 feet, and we're given the angle between, say 97 degrees. So there's side, angle, side. And of course, side, side, side means we're given all three sides. So this is what this notation means. So in section 4.2, we will look at the law of sines. Section 4.3, and in a different video segment, we will look at the law of cosines. Now, both laws are relatively easy to apply, which is kind of amazing because we spent almost an entire semester talking about right triangle trigonometry, but as soon as we look at more, let's say, complicated cases where we don't have right angles, the formulas are actually relatively easy to use, with one exception. And not only is an exception, it's a dangerous case. I'm using the word dangerous on purpose. The case side, side, angle. And I'm going to write this so that you're most likely to remember this. I'm going to go to a big bold red. This is danger. I'll put danger here. I'll even use some of my fantastic drawing skills to draw the ugliest skull and crossbones that I can imagine drawing. And I'm doing this on purpose. You're thinking, oh my God, he's wasting our time with his drawing. I'm not really. I'm trying to save you ahead of time. From some really important grief here, or some serious grief. The case side, side angle is potentially difficult, and the problem with it, it's not just difficult, is students tend to lose a lot of credit on exam questions involving the side angle case because of an oversight that is completely unavoidable. Okay, so when we get to that problem of the side angle case, I'll let you know, and I've got a device that will protect you from succumbing to or becoming a victim to this dangerous case. Okay. So let's go way back. That means let's talk about what is in fact the law of sines. Well, to do this, we need to start with a convention that we or build upon a convention that we talked about before. So here's a triangle, an oblique triangle. Here's an oblique triangle. Give me a second to draw it. And one more side. Let's see, here we go. So we have an oblique triangle where we have no right angle. And what we're going to do is we're going to use capital A, capital B, and capital C for the vertices of the triangle, and small a, small b, and small c for the sides. Okay, just like we did before. So just like before, we can put the angles anywhere we want in the triangle. Let's say A is here, B is here, and C is here. But once we've decided where the angles are, the lengths of the sides, small a, small b, and small c, are completely determined. If A is chosen, let's say, is this lower right-hand angle, then small a, the length of the side, is opposite that. If B is chosen as the lower right vertex, if you will, the angle corresponding to the lower right vertex, then the side opposite of that is designated for small b. The side opposite angle capital C is small c. So this is how we decide to standardize our notation for oblique triangles. So what is the law of sines? It's a very easy law to write, the law of sines. Law of sines. It's actually 3 equations written in one line. Here's the law of sines. It says the sine of the angle A divided by the side small a is equal to the sine of B over small b equals the sine of angle C over small c. It's an incredibly simple law to write out, considering some of the identities we've looked at in this course are pretty long. It's a very, very short way of writing 3 equations. And what do I mean by 3 equations? Well, here's one. Sine of A over A equals sine of B over B. Here's another one. Here's another one. And a third one would be when you take the sine of A over A equals the sine of C over C. And you use one equation at a time to solve for the missing sides and angles in a triangle. But it's an outrageously simple law to use. Let's go back and figure out how much lumber's in that tree. So I'm going to halt the video, and I'll be back in a second. So I stopped the video so that I could cut and paste from earlier in the lecture the problem we want to consider now. Suppose we consider the question we looked at, or problem we looked at before, find the length of the tree. Well, what kind of information is given? Okay, that we are given the 22 degrees, that's an angle. We're given 104, that's another angle. And we're given a side that's between. So this is one of the 3 cases for the law of sines. So this tells us we're going to use the law of sines. Okay, just so we don't get too far ahead of ourselves, look above. The law of sines has these cases: 1, angle side angle; 2, side angle angle; and 3, the case we're going to spend most of our time on, the danger case, the potentially dangerous case, side angle. So we are looking at angle side angle, angle, side, angle, which was the first case, angle, side, angle. So watch your eyes, I'm flipping around here. So now that we know we're using the law of sines, we start hunting for the thing we're looking for, and that's the height of the tree. So what I'm going to do is I'm going to label the height of the tree as, say, it really doesn't matter what letter I use. I'll use, let's say, small a. And if I do that, then 22 is capital A. And I can go ahead and call 104 C or B. And the side we're not interested in is small c. And we'll call angle then B. The missing angle is at the top of the tree. And we can go forward. Now, if this weren't a practical problem, if this were just the problem of finding the rest of, or solving for the remaining pieces of a triangle, we would just go through and hunt for those things using the law of sines. But we're looking for exactly just one part of this triangle. We're looking for small a. We're looking for small a. Okay. So if we're looking for small a, we're going to use the law of sines that involves a. So we're going to use sine of a over a equals, and we're given angle C, so we're going to use sine of C, and then so we're going to have to use C. Well, that's a problem. That's a problem. The problem is we don't know C. We don't know small c. Okay, so I would rather use the sine of a over a. We're stuck with that because we're going to need to find a, so we got to use sine of a over a equals sine of b, the angle at the top of the tree, over b. Okay, and we're given b. We're given b is 150, but we don't know angle b. That's very simple. Angle b is very, very simple to find. With nothing more than a little bit of geometry. So angle B, what is angle B? Well, the sum of the angles in a triangle is always 180 degrees. So B has to equal that 180 that they have to add up to, minus the 22 from the angle of elevation, minus the 104 for the tree angle, if you will. So B has to be 54 degrees. So I'm going to put 54 degrees in brackets up there. Brackets to remind me that that's something I found. Okay, then I'm going to use that 54 degrees to find what I'm interested in. So let's go back to the law of sines. The law of sines says the sine of a over a. Well, I know that a is 22. So the sine of 22 over the thing I'm looking for, a, equals the sine of b, and I found b is 54, so it's a sine of 54 degrees over b, which was given to be 150. And check it out, there's an equation that has only one variable in it now. Cross multiply a sine of 54. This kind of equation is called a proportion, and in algebra we learned that with proportions you can cross multiply. And we keep the equals. Okay, so we get sine 22 times 150 on the right-hand side, and a times sine of 54 on the left. Divide both sides by the sine of 54, so we get 150 times the sine of 22 degrees, divided by the sine of 54 degrees. And we simply put this into our calculator. If you put this in your calculator, make sure your calculator's in the degree mode. You get a is about 69.5 feet. So there's 69.5 feet of lumber in this tree. That's not the height of the tree. That's not the distance from the ground up to the tree. That would be a vertical distance. Okay, it's actually the length of this tree. Okay, so that's the idea, is to be able to solve more realistic types of problems using trig, where we were only able to use or solve right triangle or problems that involved right triangles. Let's solve another problem. Let's do another example. So for example, solve the triangle. Solve the triangle, and we're given that A is 40 degrees, B is 60 degrees, and let's say small a is 4 feet 4 inches, just 4. Well, so I'll give it some dimensions. So 4 feet. Now we are free to draw the triangle any way we wish, but what we're going to do, and this is not in your textbook, this is my way of protecting you from the dangerous case coming up. What we're going to do is we're going to try to draw the triangle every time. We're going to try to draw the triangle the same way. This is not going to be the case side angle, this particular problem, but I'd like you to, if you want, to try to protect you from the difficult case, or from losing points on the difficult case, is try to draw the triangle the same way every time. So what is he talking about? Okay, and so here's what I'm talking about. When you're drawing the triangle, and if you're given an angle, and the only case you'll not be given an angle is if you're given all 3 sides, but if you're given an angle, draw the angle in the given angle in the lower left-hand corner every time. Every time. If you're given an angle, draw it in the lower left-hand corner. Well, we're given 2 angles, so put one of them in the lower left-hand corner. So I'm going to put that 40 degrees, or the 60 degrees, I'm going to put the 40 degrees in the lower left-hand corner. So here's 40 degrees. Okay. Then, if you're given, if possible, leave the horizontal side empty, if possible. Okay. Well, since we're only given one side, that's very much possible. So try to leave the flat part, the horizontal part, free, empty. Okay, so I'm going to put in 4 as the side opposite 40. I kind of have to, because if A is 40 degrees, capital A is 40 degrees, I need to put opposite that 40 degrees, small a. Okay, so I have 2 sides that I have to solve, and I have an additional angle that's given. You can put the additional angle anywhere you want now. Okay, so let's say we put it up here. Okay, in fact, if possible, try to leave the horizontal side unlabeled. Don't put a length on it, if possible. If not always going to be possible, and try to leave the angle opposite the given angle empty. Okay, this will all make sense when we get to the side angle case. Okay, so if you're given an angle, put it in the lower left-hand corner. If you're given 2 of them, put one of them in the lower left-hand corner. Leave the horizontal side blank if possible, and leave the angle opposite that on that same horizontal side, or containing that same horizontal side, leave it empty too. So leave the angle in the lower right empty if you can. Okay. Believe me, this is going to be worth your while to do this. Okay. So the next thing to do is to determine which case we have, because sometimes we're not going to use the law of sine. Sometimes we'll use the law of cosines. This is the case where we're given a side, an angle, and an angle, and the side is not between the 2 angles. So this automatically tells us that we're going to use the law of sines. Okay, so we have 60 degrees as that angle sort of on top, and that's B. So small b has to be the horizontal side that we left blank. There's only capital C and small c left for the remaining pieces, so we'll put them in, and we'll start hunting. We'll start looking for those remaining items. Well, it's pretty clear what the angle C should be. Since we're given all but one of the angles in the triangle, C has to be 180 minus 40 minus 60 degrees, and that's 100. So C has to be 100 degrees. Oh, no, C has to be 80 degrees. Sorry about that. Oh, my goodness. I do not know where I got 100. C is 180 and minus 100, so C is 80. Sorry about that. So I'm going to use our earlier convention. I'm going to put this, as I find stuff, I'm going to put it in the triangle. Then I'm going to put it in brackets to remind me that that's stuff that I found as opposed to stuff that was given. Okay. So next, let's hunt for either B or C. B or C. So I'm gonna hunt for B. I'm gonna look for B. So if I'm gonna use the law of sines and try to find B, I'm gonna use the 40 that's given. So I have sine of 40 over 4, sine of A over A, and I'm using 40 and not 60 because I know 40 and I know the side opposite 40. I'm not going to use 60 and the side opposite 60 to start this out because I don't know what B is. Okay, but now I'm going to use 60 and B because I want to find B. So you start out the law of sines with an angle that's given, or an angle that you know, and a side opposite that you also know. You start with a pair of pieces of information, an angle aside, that are opposite one another. Okay. So then we solve this equation for B. If you cross multiply, you get B times the sine of 40 equals 4 times the sine of 60. If you divide both sides by the sine of 40 degrees, you get 4 times the sine of 60 over the sine of 40. And for the rest, you just put into your calculator. B is then approximately equal to, and I rounded to one decimal place, B is about 5.4. Let's say feet. So I'll put that in. 5.4. Okay, so there's only one thing left. There's only one thing left to find, and that is small c. So once again, I'm going to recycle that sine of 40 that I started with over 4, because those were things that I knew that were given. I'm not going to use sine of 60 and 5.4 because I rounded off b. And if I use the rounded off b to find c, I'm going to be kind of compounding the error I introduced by rounding off. So I'm going to use the 40 and the 4 because they were given to me to be accurate. Now I'm going to go for c. So I'm going to use the sine of 80, which is c, over c. So I set sine of 40 over 4 into equals the sine of 80 over c. Once again, I have a proportion, two fractional expressions equal to each other, so I just cross multiply. Get that nice result that I can use with about proportions. So c times the sine of 40 equals 4 times the sine of 80 degrees. Divide both sides by the sine of 40 degrees. Sine of 40 degrees. Put this into your calculator and press enter. You get c is approximately 6.1, just rounding to one decimal place again. Then I would go up to my triangle. I would put in brackets 6.1. The reason I would put all those things in the triangle is if this were a test, I'm going to want to come back if I have any time left and check my answers. So I would look at the things in the brackets as things that I found and that need to be checked. Things without the brackets don't need to be checked because they were kind of given to us. So that's how the law of sines works. The remainder of this lecture, and we have quite a bit of ways to go, the remainder of the lecture is going to be in explaining how to deal with the case side angle. Okay, and it's not difficult. It just takes it's just a bit more complicated than the others the other cases. The other cases are very simple and generally don't give students any problems. So let's take a look at a really close examination of the side angle case. That my drawings get so bad. That dangerous case. Ugly skull and crossbones case. Okay. I'll even make our skull and crossbone have eyes and eyebrows there. And maybe a little nose. Okay. So, forgive me here. But you're probably going to remember this more because it's kind of corny. Okay. So, given, let's say A equals 30 degrees, small a is 1, and small b is 2. A real simple set of things that are given to us. Let's draw a picture. Now, regardless of whether this is the case, side angle, or any other case, try to always draw your triangle the same way. Every single time, draw your triangle the same way. Draw your triangle, if you're given an angle, draw it in the lower left-hand corner. And since we are given an angle, I'm going to draw it in the lower left-hand corner. Okay, so, and try to draw your angles approximately equal or approximately accurate. You don't have to get a protractor or anything like that. Try to draw them so they're approximately correct. And let me do that side again. In fact, I'm going to redraw the whole thing. So here's the side, the horizontal side. Here's 30 degrees. Around about 30 degrees, like that. A second here. And we need one more side. Here we go. Okay, so I'm going to try to draw every single time. If I'm given an angle, I'm going to put it in the lower left-hand corner. If I'm given more than one angle, one of them goes in the lower left-hand corner. Okay. Okay, so as soon as I do that, that A equals 1 has to go opposite. Okay. Now that angle on the other side of A on this that still corresponds to the horizontal side, I want to leave that blank. Okay. Well, I really don't have a choice because I'm not given any more angles. I want to leave the horizontal side blank. Try to leave the horizontal side blank is something that you're going to find every time if you can. Well, if you're going to do that, the only place that small b can go is along the adjacent to angle A. Well, if that side is that of length 2 is small b, then capital B needs to be the lower right hand angle. Capital C is the only thing left for the remaining angle, and small c for the unknown side. Try to do this every single time. Angle given lower right, leave blank the horizontal side if possible. Now this is the case, side angle. Side angle. This is definitely the case. Side 1, side 2, length 2, and angle 30 degrees. Okay. The next thing is that you will always try to find the angle in the angle B. It may not be B symbolically, but try to find that missing angle on the horizontal side. Okay, so let's do it. Let's use the law of sines. The law of sine says I have the sine of 30 over 1 equals the sine of the B that I'm looking for over 2. Okay, cross multiply. So I get 1 times sine of B equals 2 times sine of 30. In this case, we really don't need a calculator because we know the sine of 30 is 1/2. You can use your triangle, or you can use your calculator for these law of sines problems on the test, definitely. Well, this says the sine of B is 1. Okay, well, if we take the inverse sine to solve for B, we'll get b equals 90 degrees, even though we know that the sine of 90 degrees is 1 in this course. We've learned that already. So b is actually 90 degrees. So our triangle actually looks like this. This is a very important thing that's happening here. Its importance will come up soon. Our triangle is actually a right triangle. We found that B is a right angle. A was given to be 30. C has to be 60. Okay, because we have a 30, 60, 90 triangle. We were given that small b was 2 and small a was 1. And we would use the Pythagorean theorem in this case to find radical 3 for remaining side. We have a 30, 60, 90 triangle. Okay. Now, this case, in this series of examples that we're looking at, this case was very, very carefully chosen for us to look at. Because what we're going to do is we're going to create the problem situation by taking this same example and just change one thing a little bit. Okay, so what am I talking about? I want to look at now, given where small a and small b are still 1 and 2, but angle A is increased by 10 degrees. Okay, so our new problem, we're going to leave small a and small b alone, but A is going to increase by 10 degrees to be 40 degrees. So small a is still 1 and small b is 2. I think I had it with small a. Yes, small a is 1 and b is 2. Okay. So I want to redraw the original problem with the 30 degrees for A. So give me I'll be back in about 1 second. So here's our triangle from just a few minutes ago, a few seconds ago. Here's what the solution was when that A was 30 degrees. Now we're increasing A by a little bit, just by 10 degrees, but we're not going to increase the 1 or the 2. What's going to happen geometrically or physically if we try to do this? Imagine increasing the angle A to 30 degrees while keeping 2 and 1 the same. I'm going to try to draw that in. I'm going to increase A by 10 degrees. Okay. While still keeping the side of length 2 on that side that contains that angle. Okay. So let me clean this up a little bit. The 2 used to be here. I've increased the angle by 10 degrees, so this is now 40 degrees. This is still side of length 2. The side opposite A is still of length 1. What's the problem? The side opposite A has length 1. What's the problem? The problem is it's not going to reach the horizontal side. Okay, if the drawing is a little cluttered, let me get rid of the right angle, get rid of the B. All I'm doing is I'm increasing the angle A from 30 to 40 degrees. So I just made it a little bigger, but I'm not changing 2 and 1. Before, when A was 30 degrees, the side opposite was just barely long enough to form a right triangle. It was just barely long enough to form a right triangle. So if I increase A by 10 degrees by any amount, that side of length 1 is just going to be left dangling. There is no triangle formed. There is no triangle formed. It's impossible to form a triangle with this given information. Now that's a little unsettling. So how are you supposed to figure that out on a calculator? Or yeah, on a calculator, on a test. You can't draw these things with extreme precision to determine, well, there's no triangle drawn here because I can't draw it. This is not the dangerous case for the side-side angle case. Your calculator will give you a message that'll tell you that there is no triangle possible. So let me show you how that happens. The dangerous case is coming up. Let me show you how you can determine without any problem at all that there's no triangle formed. You start the problem by not making any assumptions at all about whether a triangle is formed or not. You just draw the way I instructed. You draw the information given so that when you do it, that the angle that you're given is in the lower right hand corner. So we were given A is 40. Make no assumption about there existing a triangle or an answer or not existing. Just try to go with the assumption that there is a triangle. So if A is 40, we're given small a is 1. Leave the horizontal side blank. We're also given 2 for small b, so B, capital B has to be lower right. And there's capital C and small c. And so we make the assumption, we don't make the assumption that there's no triangle formed. In fact, we do the opposite, assume there is a triangle formed. Then use the law of sines to try to find the angle B. The sine of 40 over 1 equals the sine of B over 2. Cross multiply. 2 sine 40 equals sine of B. I guess I put the sine of B on the other side before. Doesn't really matter. Let's see, 1 times sine of B is sine of B equals 2 sine of 40. And if you compute the right-hand side, you get the sine of B equals 2 times the sine of 40, turns out to be 1.285 ... Goes on and on and on. This is your calculator trying to tell you that there is no solution possible. There's no triangle formed. How can that be? What is the maximum value of sine or cosine? It's 1. This is impossible. Sine cannot be greater than 1. So, no triangle is formed. No triangle is formed whatsoever. Okay, it's not a difficult case. When you end up with the sine of the angle opposite that angle A that you put in the lower left-hand corner, the sine of the angle in the lower right-hand corner is more than 1. There's no triangle formed, and you stop. That's the answer. There's no triangle possible. Okay. So now, what I'm going to do is I'm going to consider, this is the dangerous case. You'll see why it's so dangerous. So given, instead of adding 10 degrees to 30 to make it 40, I'm going to take 30 degrees and I'm going to subtract 10 degrees. So now A is 20 instead of 30. Small a is 1. Small b is still 2. Okay, so just as a reminder, what happened in the first case when we had that right angle solved. Okay, so this was the first case where we had A was 30 instead of 20. And small a was 1, small b was 2. And it turned out there was a triangle formed. There was a triangle formed. Now, imagine that we decrease 30 by 10 degrees. Okay, I'm going to try to draw that in here. But we leave 2 and 1 the same. The other sides of length 2 and 1 the same. So we're going to now decrease by 10 degrees, keeping length of 2 and length of 1 for the other side. So the length of 1 previously, when we had 30 degrees, formed one triangle of a right triangle. So if I decrease the angle by 10 degrees and make it 20 degrees, and I still leave that side of length 1 for that remaining side, and we'll push down this way past the horizontal side. So we'll have to really lift it up here and increase that horizontal side. So we're going to get a triangle formed. Okay, so here's the angle C, here's the angle B. So let's solve the triangle and see what happens. Okay. Now, when you're doing this in practice, you don't have to superimpose triangles and stuff. I'm trying to make an important point here toward the end. So let's assume we're drawing this from scratch. Oops. Let me draw this from scratch. Keep doing that. All right, here goes. Here's the horizontal side that's given. If we're given an angle, and we are, let's draw it in the lower left-hand corner. So there's A, and there's 20 degrees. So if we choose A at the lower left-hand corner, we're also given small a, so that's got to go opposite. We're given B is 2. You could put it down in the horizontal side, but don't. Leave the horizontal side blank. Leave the horizontal side blank, if possible. Okay, for side-side angle, it will always be possible. So for the dangerous case, it's always going to be possible to set your triangle up this same way every single time. Okay. Now, let's hunt for the angle B. We always look for, if possible, and it will always be possible for the side-side angle case, we always hunt for the angle in the lower right-hand corner. It may be labeled as C or A, in this case it's B, but you always go looking for that angle. So set up the law of sines. Sine of 20 over 1 equals sine of B over 2. Cross multiply. 1 times sine of B is sine of B equals 2 times the sine of 20 degrees. If you multiply 2 times the sine of 20 degrees, you end up getting, I got 0.6840. It goes on and on and on and on and on. Okay. And this is perfectly possible. The sine is less than 1. So we use what we did in section 4.1 to find the angle. We don't use the sine function. We use the inverse sine function. Whenever you're trying to find the angle using a trig function, use the inverse trig function. When you're looking for the angle, you use the inverse trig function. If you know the angle, you use the trig function. But if you're looking for the angle, you use the inverse trig function. So inverse sine, B is the inverse sine of 0.6840, etc., etc., etc. Okay. And what I'm going to do is I'm going to round to no decimal places. So I'm going to, just to make things simple for us, B is approximately 43 degrees. I think it's 43.2, but we'll just round off to no decimal places. Okay. So things are going very well. This is the dangerous case, but almost 100% of students are not going to make a mistake at this point. This is not where the mistake happens, okay? So what I would suggest is put in the angle that you found in a brackets in the lower right-hand corner, and then look for the remaining things. Well, we don't know the angle C yet, so to find the angle C, it's very simple. The angle C has to be 180 minus the 20 that's given, minus the 43 degrees that we found. So C is approximately equal to 180 minus 20 minus 43, and that's 23. Not 23, it's 117, sorry. Sorry about that. I'm not doing real well with my arithmetic today. So this is 117. Okay, so let me put that 117 up there. 117. Okay, this again, almost no students make a mistake at this point. Almost everybody gets this right at this point. This is not where the mistake happens. So let's look for small c. So we're going to use 20 and 1, sine of 20 over 1 equals sine of 117 over c. So again, sine of 20 over 1 equals the sine of the 117 over small c, cross multiply. C times the sine of 20 equals 1 times sine of 117 divided by sine of 20. So C equals sine of 117 divided by the sine of 20. Then let your calculator compute that for you. So enter this into your calculator. C is then approximately, what did I get? 2.6. 2.6. And again, almost 100% of students will get all of this right. Now here's the bad news. The bad news is this. While 100%, almost everyone, almost 100% of students will get this right so far, if this were a 20-point problem on a test, 10 points are lost. And there's nothing wrong yet, but 10 points are lost. There's something big missing. There's something big missing. Now let me show you what went wrong, or what's gone wrong. Here's our triangle that we just solved. Now let me get rid of the things. Let me erase the things that we just found that were in brackets. Let's get rid of the small c, the b, and the c. And this is where we started. Now, in drawing this triangle, I made a big assumption about the triangle. We weren't given angle C. We were not given angle capital C. So why did I draw the, or small c, why did I draw that side tilting the way I have it, the side of length 1, the side from B to C? Why did I draw it tilting that way? Well, so just to give you more of an idea of what I'm talking about, imagine that the side of length 1 is a door and it's on a hinge, and the hinge is oops, I have the eraser on. The hinge is right at C, so I can swing that door, and I'm going to swing that side from B to C in a circular arc this way, and I'm going to reattach it over here. And when I do that, I'm going to put it in red. It'll be right here. So all I did is I swung that side of length 1 in a circular arc and reattached it to the horizontal sine. And I did that without affecting anything that was given to me. Nothing was affected. Small a was 20. B, the angle B, capital B, moved over, but it wasn't given to me, so I could do that. And I didn't change the side opposite A, but I formed a very different triangle. The triangle that's now formed is this red triangle that I'm going to put in. There's an entirely separate triangle formed by swinging that side around or through an angle and reattaching it to a new position. That new red triangle, highlighted in red, still satisfies the original stuff that's given. Okay, so there is an entirely second new answer formed. There are two triangles formed here with the same piece of the same given information. Okay. So I've put the first triangle back below our drawing here with the red second triangle formed, and I want to explain how we get that second the second red triangle, the red triangle, the second answer. It's not difficult. The most difficult part, and there's some light at the end of this tunnel. The most difficult part is realizing or recognizing that there is a second triangle possible. Now, if you've drawn the triangle the way I suggest from the very beginning, by drawing the angle in the lower left hand, the given angle in the lower left hand corner, leaving the horizontal side blank, you will always be able to get this second triangle as long as you can recognize that there is a second triangle, and that's going to come up at the very end. So let's find that second triangle. Let's find the new triangle, the red one that's missing. Okay, let's do that. Well, first let's look at identifying the new angle B, the new angle red B. Notice that the old angle B was 43 degrees. That's over here. I'm redrawing it in. If I swing that side of length 1 or over in a circular arc and reattach it, then the angle that I'm drawing now must also be 43 degrees. The angle, the little triangle that I circled here, that's an isosceles triangle. It has two angles of length 1, or two sides of length 1. So the base angles have to both be 43 degrees. So that's 43 degrees. But that's not the angle I'm interested in. That's not the angle. The angle in the new big red triangle is this angle. And that's easy to find. The new angle, which we're also going to call B, so I'm going to call it, say, B sub 2. The new angle, B sub 2, is 180 minus the original B, minus 43. Now, sometimes the problem will not have that as B that you're finding. Sometimes it'll be the new C or the new A or the new B or whatever. But it's always going to be 180 minus the angle that you found in the lower right-hand corner. As long as you if you draw your angles for your triangles for side angle the same side every time, it's always the new angle is 180 minus the old angle. Okay. Well, we also need a new C, a smaller C in that big new red triangle. Well, I found that B sub 2 is 180 minus 43. And 180 minus 43 is 137, so let's put that in. So that new angle is 137. Oh, yeah, having a hard time drawing 7. Okay. Well, small c then is very simple. Small c2 has to be 180 minus the initial 20 minus the 137. It's not going to leave much. That's 23. So that's 23 degrees. The only thing left is the new c, the new small c, which we'll call it C sub 2. And you see, it's very easy to find the second triangle once you realize that there is a second triangle. So we use that using the law of sines. We recycle the sine of 20 over the opposite one equals the sine of the new c, that was 23, over small c, c2. Okay, the old c was 2.6. The old c was 2.6. So the new c had better be smaller than that because we shortened the sides small c. Okay, so it better be less than 2.6. Now let's see what happens. So we get c2, we cross multiply c2 times the sine of 20 equals 1 times the sine of 23. Divide both sides by the sine of 20. And we get small c, 2 is, what did I get? I got 1.1 feet or whatever. Okay, so the new c is 1.1. So we got 2 separate triangles out of this side-side angle case. This is the danger that I was mentioning, is the danger, and the only danger is students will neglect to find that second triangle. Okay. So the only thing that you need as a student, the only thing you really need is an answer to the question, how can I tell if there's going to be 2 triangles? Well, in order to tell that there's only going to be 2 triangles, I want to solve one more case. Okay, and then I'll pull all this stuff together and let you know exactly when you can tell that there's 2 triangles. For this last case, it's going to look very much like this one. It's going to be A is 20, so I'm going to keep A as 20, circling it in green. But I'm going to switch the sides. The side opposite is going to be 2, and the side adjacent is going to be 1, adjacent to the given angle. Okay, this is very important. It's along the lines of showing you how you can tell if you have 1 or 2 triangles. So A is 20, small a is now 2, and small b, was it small b or small c? Small b is now 1. Okay, so I'm going to draw that triangle. Remember, you draw the triangle, so you always draw the angle in the lower left-hand corner. Always, always, always. Okay, a lot of students ignore me on this, and a lot of students lose points on this too, so I think you should always do it this way. Then, draw in the remaining pieces of information. Okay, so A is 20. It really doesn't look like 20. That's okay. It looks too much, but that's okay. A is 2. Small b is 1. C, small c. Okay. Now, before I solve this problem, I want to convince you that there is only one possible answer. There is only one possible answer. There is going to be one triangle only. How did we get that second triangle before? We took the initial side of length 1. Look back at the drawing here. We took the original angle of length, the side of length 1, and we swung it over and reattached it at the new point B, where we have the new angle B. Look what happens if I try that now. Look what happens if I take that side of length 2 and try to swing it over and reattach it to the horizontal side. Okay, so here it is. Here's the side opposite. And I'm going to try, without changing its length, I'm going to try to swing it over at length 2 and reattach it to the horizontal side. Not going to happen. It's not going to happen. It's too long to do that. I swung that side over in a circular arc and tried to reattach it, and it's too long. When I swing it over, it needs to reattach to the same side to form that new triangle. But look what happened in that second attempt at swinging. I reduced its size. You can't do that. So there is only one triangle formed, and there's exactly one triangle formed. Let's solve for that. Let's solve the triangle, and then I'll explain. Then I'll give you the explanation of how you can tell whether there's 2 triangles formed or not. I'll tell the answer now, but I'll also tell you. I'll give you the sort of formula for determining whether you have two triangles. The problem is the side opposite the given angle was longer than the side adjacent. The side adjacent to the given angle is 1. The side opposite's 2. The side opposite is longer than the side adjacent, so there's going to be one triangle formed. For two triangles formed, the side opposite needs to be smaller than the side adjacent. I'll repeat this at the end. For right now, let's figure out this last case. Let's solve for the missing. It's good practice for us. Let's solve for the missing sides and missing angles. So we're going to hunt for angle B. So we have, just as before, the sine of 20, but it's over 2 now, equals the sine of B over 1, cross multiply, so you get 2 times the sine of B equals the sine of 20. Divide both sides by 2. The sine of B equals the sine of 20 divided by 2. If you compute that, the sine of 20 divided by 2 is like 0.17, goes on forever and ever and ever, repeats, or it goes on as a decimal. Now that's less than 1, so that's okay. There's a triangle possible. Remember, if that was more than 1, we would conclude there's no triangle possible. So B equals the inverse sine of that, 0.17, whatever it is. So B, the calculator tells us it's about 9.8 degrees. Approximately 9.8 degrees. So we put in 9.8 degrees in brackets. Angle C is a super simple thing to find. Angle C is 180 minus the given angle, 20, minus the 9.8. And that's about 150.2 for C. Put that in brackets. So it's very simple to solve the triangles once you're set with the data that are given. Small c. Small c. So I'm going to recycle the sine of 20 over 2 equals the sine of C, which is 150.2 degrees over the C that I'm looking for. Cross multiply. C times the sine of 20 equals 2 times the sine of 150.2 degrees. So C equals 2 times the sine of 150.2 degrees divided by the sine of 20 degrees. And your calculator will give you C as about 2.9 inches, feet, whatever the units are for length. So 2.9. So it's very simple to use the law of sines once you're secure in the data and stuff. So how can you tell if you have two triangles formed? It's not difficult. When you draw your triangles, you're always going to draw them the same. So you put the given angle in the lower left-hand corner. So I'm sort of doing this in a generic case. If you do that, then you'll always put the side opposite that in the triangle, because if you're given side angle, you'll always have the side opposite the given angle given. Now you're also going to be given another side. Don't put it on the horizontal side. Put it on the non-horizontal side. So you're always going to have your triangle pictured this way. The only way you can have two triangles formed is if the side opposite the given angle is shorter than the side adjacent. there will always be two triangles formed if the first angle that you find then is less than 90. If this angle is less than 90 degrees, there will be two triangles formed. So how do you know that there are two triangles formed? First, the side opposite the angle that's given has to be shorter than the side adjacent, and the first angle that you find needs to be less than 90. So if you had a case where it was, say, 5, 3, and you found that the angle was 20 degrees, and you were, say, given 15 degrees, and you found the first angle to be 20 degrees, there are two triangles formed. Automatically two triangles formed. Okay, so two triangles formed. Two triangles formed. Formed. However, if you had started out this way, 5, 3, 15 degrees, and you found that this was 20, there's only one triangle formed. So, just to make sure, there are two triangles formed when the side opposite is shorter than the side adjacent, and if the first angle you find in the lower right-hand corner is less than 20, there will be two triangles formed. And you form those triangles the same way I did, that second triangle, the same way I did a couple of examples ago. You swing the side opposite the given angle over and redraw a new triangle and find the remaining bits of information. Okay. Okay, now that ends our section. This is probably going to have a very short, frustrating period for you on homework. Very, very short. You're going to get very good at this. My students traditionally have gotten very good at this tricky case, side-side angle, very, very quickly. And it's a little frustrating at first. It's a little frustrating, but use the formula I gave you for determining whether you have two triangles formed, and you should be just fine. Okay, and as usual, I am looking forward to talking with you all again very soon.